I'm going to share the screen. All right, so we are sharing and recording now. And all right, so let's kind of review where we were. This is the ML pipeline, I believe, right? That was the script that we were using. So let's go to ML pipeline. Okay. All right, so I'm going to take a look. Got our data here. Right, we did all the steps. I'll kind of quickly go through these. There's our Euclidean distance. We've talked about it. Here's the KNN. I'm going to use a different approach than what I was writing the last time around. Instead, we're just going to take the average, and then after that, we want to basically, do the performance metrics over here. All right, so let's start from the beginning. I'm going to restart the kernel. I'm going to go to cell, kernel, sorry. Restart and clear the output, load it from scratch. Okay, so we should be ready. So I'm going to run it again, load the libraries. Remember okay, it's done. Parameter is the closest 5, right? K equal 5. Then we loaded the iris dataset, iris from iris.csv as a text file. You always want to print the shape. So we have 151 by 5. Print the data frame and from pandas. So we can see really quickly, our very familiar data set, sepal length, sepal width, petal length, petal width, and the species. Okay, then we're going to proceed here to do slicing, right? So all the rows from 1, and then all the columns up to the 4th column there, 0, 1, 2, 3. Okay, so you can see now X is 150, 4. And there's the data, you can visualize it. We can look at the type, that's a good idea. NumPy is kind of what we want. Shape, 150, that's Y. Okay, NumPy array. Then we have the issue that these are strings. So I had discussed the label encoder, right? In a sense, these filters are kind of nicer, I think, than the Weka ones because they're easier to find. We use SKLearn a lot for these kinds of things. And even when we start doing the deep learning things, we can continue to use SKLearn for a lot of these tasks. So I've got the data set there. Now I'm going to do the label encoder. We had discussed this already as well. This just changes the values, as you can see, from words to numbers. Okay, remember that all X and Y data need to be numbers from now on. We can't have strings. Weka has some flexibility, but this won't be forgiving in that sense. Okay, so then, NumPy array. I always print the shapes. I notice in your homework assignments, you guys would print the actual values in the vectors, even though it was a huge image. That I can see why you're doing it, but eventually you'll see that it's more useful and meaningful to print the shapes. You just kind of live by the shapes, because otherwise you just see random numbers that don't make sense. So shapes are a big friend, and this is not going to go away. All right, then train, test, split. You'll pretty much can use this function. Split the data. You guys, we've discussed this already. We're going to have 4 matrices and vectors there. X train, Y train, X test, Y test. The tests are used to evaluate our model. The train ones are used to train the model. Usually we give it X, it predicts something, and that Y pred needs to be compared with Y real. So this is actually where I'm going today. It's kind of what I needed to conclude. And so which is really important and leads us to performance metrics next week. So now I have my data sets. You can see 120 are for train, 120 here, and then 30 are left for evaluation. So the way that I always tell students, if you're going to build this model and try to sell it to the government, you got to sell them on this idea of the 30 samples and the performance on it, okay? All right, so KNN is definitely, I like to start. I don't discuss in this class. It's not possible, actually, to discuss every single algorithm in machine learning. You'd probably hate me for it also, right? But I will discuss some of the major ideas like Bayesian, trees, and definitely neural nets is something that we will spend 1/3 of the class on. All right, so the Euclidean distance, I've already discussed this, so we've talked about it quite a bit. And then we've got the KNN algorithm itself, which is just these lines of code. Yes, Henry.
What ratio should the test data be with like the training data or like the validation data?
Train and test. It depends. So I haven't discussed something called tenfold cross validation, even though maybe you guys saw it in WECA already. I need to talk about that. But currently, train test split is just 80 to 20. That's kind of how people do it.
If we're able to get another test set, would you just split between the tests?
You mean like a train, validation, and test?
Yeah.
You can have that. Some people do training, then they kind of want to do like parameter exploration with the validation, and then they finally evaluate on the test set.
What would the ratio be?
That's a good question. I mean, I don't like to do that, to be honest, but 60, 20, 20, I mean, that I'm just, I always just,
Training data, not test.
well, the thing is, it's a trade-off, right? So if you take from the train set, then the model hasn't seen that many examples, so it's gonna do worse on the test set. It's just, you gotta feel it out. But in general, you don't always need a validation set. Sometimes train and test is more than enough, okay? It just depends on the problem. All right, so I'm pretty sure this is where we left off, where we were stuck, okay? So I'm just gonna go over this one again. You gotta think, I did this, and I was playing with just predicting one value, but really, I'm going to kind of delete this because you already have it in the video if you want to get it, or on the GitHub. And really, I'm just going to concentrate on this part here, which is really, now we want to evaluate performance, right? So that means all 30 samples need to be evaluated, basically. Now, keep in mind, again, KNN does not do training. That's why it's called a lazy algorithm. You're just basically comparing the 30 test samples to all the samples in the train set. However, as we move to neural nets and things like that, there will be this idea of training, okay? But here, there's no training. All right, so let's start here. So list of preds is a list of the predictions that I'm trying to make, right? So I'm gonna take 30 test samples. So you can see for I in range of length X tests. We know that there are 30 test samples in here, right? The vectors of size 4. We're gonna serve each of those vectors into the predict function, right? And it's gonna give us a Y pred, which is for this test sample of 4 features, we got Y pred. It's class Setosa, Virginica, Versicolor, right? That's in Y pred. Then notice that what I'm going to do is I'm just going to add that prediction into a list called list of preds. Does that make sense? And then notice that after that, what I'm going to do, let me move this code to a new cell. So it's more obvious. You can see here, all I'm doing is I'm going to take this list of actually, keep that back. This list of preds, which is a Python list, I'm just going to run it through np.array to make it a NumPy array. That's all I'm doing, right? And then now I'm going to have preds list np and Y test. So in the test set, we have 30 samples, right? That means we have 30 real labels that we know what these labels are for those 30 samples. And this list up here is the prediction. So all I'm going to do is compare them, basically. You guys see that? That's my objective here. Okay, so now I'm going to go, as I said, I'm just going to delete this so it's not confusing. And I'm going to delete that. All right. So I'm going to, now the key thing is I need to send these test samples to the predict function. The predict function is where the KNN happens. It takes just one sample and compares it to all 120 samples in the train set, right? Calculates the distances and everything. So we've talked about that. So you get one test sample. I'll kind of repeat this. These are like the 4 or 5 lines of KNN. So we do a list comprehension for X in X train. We grab every single one of the 120 samples, right, of the train set, and we pass it to the Euclidean function with the current test set. We compare that distance, and because this is a list comprehension, it just gives us that distance, and we populate the list called distances, which will have all of those values. Do you guys see that? All 120 distances will be here. Does this make sense? Okay. Now, once you have the distances, NP-ARC-sort is something we had also defined. What does NP-ARC-sort do? It sorts the data, but it doesn't return the value. It sorts by the values, but what's returned is actually the indices. This is a very convenient thing in machine learning, right? Because that's really what you want. You want the indices because you're going to grab those indices from the Y vector base. Okay, so that's what KNeighbor is. Now here, this little thing is just slicing. Because this is a tensor, you guys should know what this is, right? What does that mean? From the beginning to K, where K is 5. Because they're sorted, it takes just the 5 closest distances, right? They're sorted in ascending order. Got it? And this is how I get my 5 IDs that I need to look up. Right? Okay. So now I have those 5 IDs in KNeighbors. And then here, another list comprehension for I in KNeighbor indices. I grab the indices and I'm going to look them up in Y train. And that's going to basically return the labels. Okay. The predicted labels. So here I have then the labels. So I have 5 labels here. Now the trick is, before I was doing this, and this works, but I kind of wanted to do something a little bit more intuitive. So this will still work. So I'm just gonna do that and keep it in there as a comment. Okay, so I've just commented out. Another thing you can do is just take the average and return that. And that should also be the same thing. We really can do it. Let's just say result is going to be int, right? And then what do we need? We need to take labels and do what to labels? np.array, because labels currently is what? It is a Python list, right? And we're just going to convert it to a NumPy array for convenience. Okay, and so that gives me now labels underscore np, and then I can just try something like labels underscore np dot mean. You see what I'm saying? So I'm just taking the mean. Does that make sense, guys? So now res is the thing that I'm going to return. So I'm going to do return, sorry. Return res, basically. Questions? Do you guys see it? I think this is more intuitive, so this is why I changed it. And it's actually how I did it in the code that I provided for the mini project. So I also wanted to be consistent with that. So actually, the way that this should work is np.mean and then labels np. Just like that. All right, so basically, as I said, we produce a list of labels. I convert the list of labels into a NumPy array, take the mean of it, and the integer is just what? Because it's going to be like a float. So int just makes it integers. It's like a rounding trick. All right, questions? Yeah, that's it. So now let's proceed to see if this works. So I'm going to go ahead and hit run here. Okay. And now remember, this is going to create a list. Let's see if it errors out first of all. Okay, no errors. That's always a good thing. And then now what I did is I have these two prints, right? So I just wanted to do a qualitative analysis. Qualitatively, what do you think? So the top list is the predictions and the bottom list is the real. So if we take a look at it, what I'm saying is it predicted these, right? So this top row and these are the real ones. And I tried to align them so that it was easy to see. I believe there's 30 here, right? So there should be 30. Yeah, look, I think it's 30. So for the first one, is it correct? Did it do well or no? Did well, right? Second one, did well, did well. Ah, error. Do you see that? It predicted one, it was really two. Do you see that? Yes.
Is this where you set your data for the loss function?
No. Performance metrics. Loss functions are something else for training. We haven't gotten to loss functions, but we will get them when we get to linear regression.
I ask, what's the loss function?
Sorry?
Was there a loss function in performance?
So the loss function is something that you're trying to minimize that governs the behavior, the relation. So the predicted minus the real, and you square it, but during training. So to minimize the error. So it's a good question, right? So here you're comparing predicted to real. You're also kind of doing that during training, but you're trying to change things based on minimizing that difference. So sometimes, let's say, for instance, that these values got really like 5, really different numbers, right? Many, many errors. So then you need to do something with your algorithm to reduce that error so that these differences are smaller. So that's kind of what loss functions do. But we haven't gotten to that yet. It'll become very obvious when we start talking about like linear regression. That's the thing. But right now, all we're doing is measuring performance after the fact, if you will. Forget about training. There's no training here. Forget about all that stuff. We're done with the model. We just want to see how well it did. Okay, which is what you did in Weka, actually. This is the exact same thing. All right. Okay, so as I was saying, I have one error somewhere, one error here, one error here, another error here, another one here. So there's a few errors, actually, right? There's a few errors in that, like 4 or 5. But what if you had 1 million of those? It's not practical to do this qualitatively, right? But you already know how to measure this. You use the same approach that you did in your Weka classification problems. This is classification. So what are the metrics? Precision, recall, F measure, confusion matrix. Okay. So that's what I'm going to add now. And it's very straightforward, and we will use this all semester. So I have a really nice function from SKLearn that we can use all the time. So it should be in one of these. And I'm just going to copy that function, and I'll show you how it should work. There it is. So this is the function that you guys can use always to get the performance. Okay, so I'm going to just copy the function. We may need to also bring in the sklearn libraries. So I don't remember if I had done that. But this function is just some function you have available. It's called print stats percentage train test, some name. Key thing is it takes y test and y pred. Do you have y test and y pred? You do. It's actually these two things. You see that? One is the NumPy array of predicted values, and the other one is the array of real values. So those two values go in here, and after that, it does the heavy lifting for you. You can provide the algorithm, like if you want to just have a string. Notice here, it invokes something called accuracy score, which takes y test, y pred. Then the confusion matrix, there it is, y-test, y-pred. Then precision score, y-test, y-pred. You do have to tell it this, average equal weighted. And then you have recall score, y-test, y-pred, and F1, y-test, y-pred. Pretty much what we did in Weka, but in this nice little function. Any questions? All right, so I'm going to run it, and I don't remember I had the libraries. Did I have the libraries? Yeah, I don't have them. So we need to add the libraries. So those are probably in this Jupyter. So we just have to go to the very top. And it should be these, you see? Right. So just copy these 3 lines of code from that Jupyter so that we can import from SKLearn these. And I'll show you later if we do regression, SKLearn will have an R square as well. So we'll just use that. So now let's see if it works. Let's run it. Okay, no errors. That's always a good sign. And then now let's just go to invoking the function so that we can get our results. So, okay, this is what the output should look like. You can see y-pred, y-test. This is kind of what I had before. So now we should only need to call that. All right, so let's scroll down to the bottom now. And we'll wrap up with this today. So, where's... Okay, so this function actually does not return anything, so I'll get rid of that return. Let me do that. So actually, it should print all the data, right? If you guys read the logic. So it's got, I don't see anything. Okay, questions about this? All right, so now KNN is the algorithm. I'm just going to pass it. Obviously, I need to pass these correctly. So y-test is y-test, but this one should be preds, list, and p. Right? Y-pred, preds. Got it? The dimensions need to match. You have 30, 30. They should always match, but I'm just stressing that point. Okay, so let's go ahead and run it. That's it. There you go. Like magic, you have the same thing that Weka provides. Okay, you have right here KNN algorithm. Accuracy score is 0.83. You guys know what that is in a sense. The confusion matrix is right there. You can see the diagonal. We did see that there were 5 errors, right? That I kind of noticed that. And yeah, I don't have the labels like Weka does. This is something we would need to add. Okay, and precision is 0.90, recall is 83, and F1 measure is 83. Does this make sense, guys? That kind of completes the pipeline that I wanted to discuss for today, which is basically, as you can see, getting to our metrics. Make this smaller. Yeah, all this, like I said, it's just me when I was kind of giving you the steps, but really, ultimately, this is what we're always after. Some metric, right? When you guys do the second mini project, which is the competition, whoever gets the highest F1 measure wins. That's basically how it's going to work. We always in machine learning have some kind of a metric. If you're doing things with ChatGPT and things like that, like language translation, there's even more advanced metrics, like they're going to be called the blue score or glue or whatever. It's just way more. But there's always in machine learning, you don't really do qualitative analysis. You go by metrics, actually. Next week, I will actually go into what is precision, what is recall, what is F1 measure. That's actually Tuesday's lecture, basically. And then we're starting neural nets. So are there any questions? This kind of, I believe, completes the KNN algorithm. I hope you guys understood how it works. As I said, vector spaces are extremely important. I'll come back to them probably next week or the week after in relation to what is called embeddings and neural networks. And that's going to be another concept to wrap your brain around, but it's still based on this idea of vector spaces. Yeah, that's it. So go over the algorithm. I suggest you play with this, you know, like print every step. And then, as I said, you always have you now have this function, which we will continue to use, and you are able to obtain your performance metrics. All right, guys, great job on the data science WECA exercise. And then, yeah, I'll see you guys on Tuesday.